Every year in the United States, tens of thousands of kilometers of new roads are laid. More than 40,000 kilometers of roadway appear annually, and almost a third of them are made of concrete. These roads are designed to last for 40 to 50 years and withstand loads of several dozen tons. At first glance, these are ordinary highways, but behind the familiar grey surface lies a world of high technology, engineering precision, and complex production processes. The road base is compacted with the same thoroughness as the foundation of skyscrapers. Steel elements are placed with accuracy down to the centimeter, and gigantic concrete pavers, stretching for dozens of meters, work right on the construction site like industrial robots. Have you ever wondered how American engineers turn piles of crushed stone, sand, and cement into some of the most durable concrete roads on the planet? Today, Mandarin Tech offers a look behind the scenes of this process. When it comes to roads, most people automatically picture asphalt. However, in the United States, concrete roads are by no means a rarity. More than 30% of the entire federal road network of the country is built using cement concrete pavements. Yes, concrete does not always provide the same smoothness of ride as asphalt, but on key highways, the choice is often made in favor of concrete, and there are solid technical reasons for that. The service life of concrete roads reaches 34 years, which is roughly twice the operating life of asphalt pavements. In addition, concrete is significantly less prone to deformation from heat. It does not sag and does not flow under heavy transport, which makes it an ideal solution for routes with intensive freight traffic. Another important advantage is construction speed. Combined with modern continuous pavers, concrete makes it possible to build 3 to 5 kilometers of road in just one day, significantly reducing project timelines. Any construction of a concrete road begins long before the first machine appears on the site. First, a detailed survey of the future route is carried out. Engineers study the terrain, assess the strength of the soil, and the quality of the rock beneath the surface. At this stage, they calculate how much earth will need to be removed or, on the contrary, added. The possible impact of the work on the environment and traffic flows is analyzed. It is here that key decisions are made. How many lanes the road will have, how long it will be, and what method is best to build it. After the project is approved, the construction team proceeds to clear the area. Vegetation is removed, and the roadway is raised or lowered in accordance with the features of the landscape. The base must be carefully compacted in order to withstand not only the concrete surface, but also constant loads from cars and trucks. A motor grader is used to level the top layer of soil. In parallel, underground utilities are laid: power lines, water supply, drainage systems. If the road is designed without sidewalks, drainage ditches may be dug on both sides. When all underground systems are completed, construction of the road base begins, a transitional layer that distributes the load from the concrete surface downward to the soil. First, a layer of coarse crushed stone is evenly spread across the entire surface. Then it is compacted with vibratory or steel rollers, achieving a uniform and strong structure. Depending on the terrain, the expected flow of freight transport, and climatic conditions, this layer may be formed in several levels. The lower layer is made more massive and the upper layer more fine-grained to create an ideal platform for concrete. Heavy rollers continuously move along the entire length of the future road, increasing the bearing capacity of the base and reducing the risk of subsequent settlement or the appearance of cracks. On average, the compaction stage takes from 2 to 4 days. Everything depends on the length of the section and the moisture of the soil. To achieve optimal density, a water truck moves ahead of the rollers. It maintains the required level of moisture, thanks to which soil particles bond better with each other. Specialists constantly monitor the process using compaction measurement instruments, vibration sensors, and laser surveying equipment. All parameters must strictly comply with tolerances. After the road base has been fully strengthened and compacted, the team moves to the key stage, creating the concrete pavement. The durability of the entire road depends on this layer. All concrete is supplied from an industrial concrete plant, where each component is dosed with almost absolute precision. The process begins long before the concrete reaches the construction site. First, raw materials, crushed stone, sand, and other aggregates, are delivered to the plant and loaded into linear storage bins. Front-end loaders or conveyor belts are used for this. Each type of material is stored separately in its own compartments, made of steel or concrete, depending on the plant configuration. Such silos are designed for simultaneous storage of 4 or more types of aggregates. This makes it possible to quickly select the needed proportions and adapt the concrete mix to the specific requirements of the project. As soon as production of a batch begins, each material is weighed using a calibratable belt scale system. The equipment accurately determines the required amount of aggregates in accordance with a predetermined recipe. After weighing, the aggregates are directed into a receiving hopper. Its design is thought out so that the material is fully discharged without residues. This is important for the stability of the quality of each batch of concrete. The next component is water. It can come either from a centralized water supply system or from local reservoirs on the plant site. Water is fed into an independent weighing system, where its quantity is measured with high accuracy. After that, the water enters the mixer, either by free fall or through a high-pressure system with spray nozzles. It all depends on the configuration of the specific concrete batching plant. At the same time, chemical admixtures are added to the mix, superplasticizers, setting accelerators, and other modifiers. Each admixture is dosed separately through a specialized feeding system. This prevents cross-contamination and guarantees accuracy of the composition. Even the slightest deviation is unacceptable here, because the strength and durability of the future road depend on it. When all ingredients are prepared, they enter a high-performance concrete mixer. Depending on the needs of the project, the plant may use either a pan mixer or a twin-shaft mixer. Both types provide intensive and uniform mixing, allowing an homogeneous, concrete mix to be obtained in a short cycle. The finished concrete is discharged directly into the truck mixers waiting under the mixer. From this moment, a race against time begins. On average, concrete retains workable properties for 1 to 2 hours before it begins to set. During transportation, the mixer drum rotates continuously, preventing the mix from segregating or beginning premature hardening. Upon arrival at the site, the truck pulls up to the concrete paver and prepares to unload. Concrete is fed into the paver's receiving hopper through a chute or a belt conveyor. This moment requires perfect coordination between the driver and the machine operator. The feed must be continuous, without delays and breaks, otherwise defects may form on the surface. On long sections, especially when constructing highways, truck mixers line up on a strict schedule. One vehicle unloads, the second pulls up, the others are waiting in line. In modern systems, a conveyor can directly connect the mixer to the paver, speeding up the process and reducing material losses. As soon as the concrete enters the system, the slip-form paver begins to automatically distribute it over the prepared base. The machine strictly follows the specified width, thickness, and elevation of the pavement. No additional compaction or manual leveling is required. The paver is equipped with vibratory plates and forming side molds, which simultaneously compact and give the concrete its final shape while it is still plastic. Inside the machine, an auger or distributing mechanism continuously moves the mix forward, evenly spreading it in front of the entry into the forming zone. Laser sensors, GPS systems, and three-dimensional navigation technologies control every centimeter of the surface. Thanks to this, the road turns out perfectly even and exactly matches the design parameters. During the placement of the concrete pavement, the machine performs another critically important operation: automatic installation of steel dowel bars. These round metal elements are fed directly from the paver's built-in magazine and placed strictly in the middle of the fresh concrete layer. The dowels are arranged across the road at equal distances from one another, exactly within the zone of the design depth. Their task is to transfer load between neighboring concrete slabs and prevent the formation of cracks at the joints. Thanks to the built-in installation system, this process occurs without stopping the machine and without interrupting placement, even on long and winding sections of the route. Thanks to the continuous movement of the slip-form paver, so-called cold joints do not form between separate batches of concrete. As a result, a monolithic concrete slab is formed, strong, uniform, and resistant to extreme loads. It is precisely such structures that provide roads with decades of service without major repairs. The cost of such machines is impressive. Depending on size, configuration, and level of automation, the price of a concrete paver can start at $120,000 and exceed $300,000. However, with high productivity and exceptional precision, such machines have long become the gold standard of concrete road construction around the world. Immediately after placement is completed, the entire surface of the fresh concrete is covered with a special liquid curing compound. This layer retains moisture, preventing the concrete from drying out too quickly, and ensures uniform strength gain. After several hours, when the concrete begins to set, workers proceed to cutting deformation joints. Using special saws, straight lines are formed in the pavement at strictly specified intervals. These joints allow the concrete to freely expand and contract with temperature changes without destroying the surface. After several more hours, the joints are thoroughly cleaned of dust and material residues. After that, a sealant is injected inside, most often polyurethane, silicone, or bitumen-based. It protects the joints from the penetration of water, dirt, and fine particles. Without such a layer, moisture could seep inside, destroying the concrete and the road base from below. After pouring and the initial stage of hardening are completed, the section is fully closed. Workers apply yellow road markings, install warning signs, and restrict access for any transport for at least 7 days. During this time, the concrete gains its design strength. Any load during this period could lead to microcracks and surface damage. Therefore, traffic is strictly prohibited, especially for heavy equipment. Before opening the road, engineers conduct a comprehensive final inspection. Compression strength tests are performed, surface smoothness is assessed, and the uniformity of the pavement is checked. Only after all parameters are confirmed is the road officially put into operation. Although in the United States such high-tech pavers have become the norm, in many developing countries such as Peru, road construction still largely relies on manual labor. Instead of automated machines, concrete is poured directly from truck mixers through metal chutes. Then workers distribute it manually, using shovels, rakes, and long straight edges to level the surface. Dozens of people work on the site at the same time, and every step requires precise synchronization. Any delay can lead to the concrete beginning to set ahead of time. After the initial distribution, some workers use handheld vibrators, removing air voids and increasing the density of the mix. Others immediately follow them, smoothing and texturing the surface with metal trowels and hand rollers. Here, everything depends on the experience and eye judgment of the workers. Without laser systems and navigation, achieving perfect smoothness and precise level is especially difficult, particularly on long sections. Nevertheless, this method is still used in remote regions and under limited budgets, where access to modern equipment is difficult. This contrast clearly shows the difference between high-tech automation and traditional, labor-intensive methods of building infrastructure in different parts of the world. And now, a sharp turn in the route. We move to China, a country that today is considered one of the world leaders in infrastructure technologies. And what we are about to see next is astonishing even against American standards. The special feature of this project is that the road was built in one of the harshest places on the planet, in the Taklamakan Desert, a place that has long been called the Sea of Death. Extreme heat, shifting sands, and a complete lack of a stable foundation turn any construction here into an engineering challenge of the highest level. The first task was to create a level surface and fix the sand in place in order to be able to build anything at all. For this, hundreds of bulldozers were brought into the desert. The machines cut down high dunes, redistributed the sand, and leveled the surface, turning a chaotic landscape into a relatively stable platform. Each section underwent strict control. Surveyors constantly checked the height, slope, and geometry of the surface to ensure identical parameters for kilometers ahead. Excess sand was removed by conveyor systems beyond the working zone, and compactors carefully pressed the upper layer, forming a working base. However, even after leveling the dunes, the sand remained too loose. Then engineers found a non-standard solution, stabilizing it with water. It turned out that with controlled moistening, grains of sand bind to one another, forming a denser and more stable layer. Long irrigation installations and underground pipelines were deployed across the entire site. With their help, groundwater was evenly distributed over the surface, penetrating several centimeters deep. As soon as the moisture reached the required level, heavy rollers went to work. Steel drums passed over the same section again and again, squeezing out air and fixing the sand particles. The hum of the equipment carried for kilometers around. Gradually, the soft, shifting surface turned into a dense and uniform base. When the sand dried under the scorching desert sun, it became strong enough to withstand the weight of cranes, asphalt pavers, and trucks. A foundation was created practically out of nothing, only from sand, water, and precise calculation. After stabilizing the surface, workers proceeded to placing an additional soil layer. Dump trucks continuously unloaded reddish earth, which bulldozers distributed and leveled across the entire area. This layer performed several functions at once. It weighted down the base, prevented the sand from shifting under the influence of heat and vibrations, and also created a stable platform for the next stages of construction. Each section was compacted and checked again, forming a strong and reliable base. At the edge of the desert, mobile asphalt plants went into operation. Stone, sand, and polymer-modified bitumen were heated to almost 170 degrees Celsius. From there, insulated tankers delivered the hot mix non-stop directly to the placement site. Asphalt pavers distributed the scorching material in layers about 6 centimeters thick. Then, almost closely behind them, rollers compacted the pavement before it began to cool. The process resembled a perfectly tuned mechanism. The paver, the roller, the finisher moved forward in a strict rhythm. The first passes were performed with heavy steel drums, providing the main compaction. The final stages were carried out with rubber-tired rollers, which closed micropores and gave the surface a smoother texture. Temperature sensors on the pavers monitored the condition of the pavement in real time. If the asphalt temperature dropped below 140 degrees, the work was immediately stopped. Otherwise, cracks could appear. After cooling, smoothness was checked with laser systems, allowing a deviation of no more than 3 millimeters per meter. Under the influence of the desert wind, the asphalt gradually cooled and turned into a perfectly even black ribbon. The pavement was designed for extreme temperature swings, from -25 to +70 degrees Celsius. The final touch was the application of a protective sealing layer. It gave the road a deep, dark shine and reliably protected it from moisture. By sunset, the new route gleamed under the sun's rays like a dark mirror stretching through a golden sea of sand. What had only recently been a lifeless wasteland now reflected the light of progress, the result of a fusion of human endurance, engineering thought, and high technologies. After 4 exhausting years of construction, a 4-lane highway crossing the largest desert in China was completed. This project not only connected remote regions of Xinjiang, but also became a symbol of what a human being is capable of in the most extreme conditions. The engineering solution turned out to be so impressive that it earned respect, even from specialists in the United States. So, we have reached the finale of today's video. You saw how roads are created, from the concrete highways of America to the asphalt routes in the heart of the Chinese desert. All information was collected from various reliable sources, and if you notice an inaccuracy, be sure to write about it in the comments.